Say you're waiting on an important document, a contract, something that needs to be reviewed today. It arrives as a PDF. You open it, and something is immediately off. The pages are there, all 12 of them, but they're in the wrong order. Not dramatically wrong, just subtly, maddeningly wrong. Page 8 is sitting where page 3 should be. The signature block appears before the clause it refers to. The conclusion comes before the argument. You can read every word. You just can't trust the sequence. Now here's the thing. If those pages had numbers printed on them, this problem takes 30 seconds to fix. You sort by page number, read from 1 to 12. Done. If they don't have numbers, if the only way to determine the correct order is to read the content carefully enough to infer the sequence, the problem becomes slow and error-prone. You have to understand the document in order to reassemble the document, which means you can't really reassemble it without already knowing what it says. Page numbers seem obvious, trivial, even, but they carry an enormous amount of practical weight, and networks use exactly this idea to solve exactly this problem. When data travels across a network, it gets broken into packets, individual chunks, each making its own way to the destination. Different packets can take different paths. Different paths have different lengths, different loads, different delays. The result is that packets sent in one order can arrive in a completely different order. The network doesn't track sequence, it moves pieces. Reassembly is somebody else's problem. Sequence numbers are how that reassembly problem gets solved. Before a sender transmits any data, it assigns a sequence number to each piece. This number doesn't represent the packet, it represents position. It marks where in the overall stream of data this particular chunk belongs. The receiver, collecting packets as they arrive in whatever order, uses those numbers to sort. A packet that arrives early doesn't get processed immediately. It waits, held in a buffer, until the packets that belong before it have also arrived. Then the receiver assembles the pieces in sequence number order, hands them off in the correct order, and the application above never sees the disorder that happened in transit. Now here's where it gets interesting, because the way TCP, the protocol that handles this for most internet traffic, actually assigns sequence numbers is not quite what you might expect. You might assume that packets get numbered. Packet 1, packet 2, packet 3. That's a natural mental model, but TCP doesn't number packets. It numbers bytes. Every byte of data gets a position in a continuous numbered stream. If you send 1,000 bytes, and the starting position in the stream is 0, then those bytes occupy position 0 through 999. If the data gets split into two packets, 400 bytes in the first, 600 in the second, the first packet carries a sequence number of 0, and the second carries a sequence number of 400. The number doesn't identify the packet, it identifies the position of the first byte inside the packet. Why does this matter? Because it makes the mechanism robust in a specific way. Packet sizes aren't fixed. Different network conditions lead to different packet sizes, and sometimes data gets resegmented between sender and receiver. If packets were numbered rather than bytes, a resegmentation event would scramble the sequence numbers. Because bytes are numbered, the sequence numbers stay meaningful regardless of how the data gets split along the way. The position of each byte in the stream never changes, even if the boundaries between packets do. There's one more wrinkle worth understanding. The sequence number doesn't start at 0, it starts at a random number. When two machines open a connection, before any data flows, they exchange that starting number. Each side picks a random value and tells the other side, "This is where my byte stream begins." This exchange happens during what's called a three-way handshake, the brief negotiation that opens every TCP connection. Machine A sends its starting sequence number to Machine B. Machine B responds with its own starting number and an acknowledgment of A's. Machine A acknowledges B's. 3 messages, both sides know both starting points, data can flow. The randomness isn't arbitrary. If sequence numbers always started at 0, an old or delayed packet from a previous connection, one that happened to be floating around in the network, could arrive during a new connection and be mistaken for current data. Starting from a random number makes this collision vanishingly unlikely. The starting number also serves a security function. An attacker trying to inject forged packets into an existing connection would need to guess the current sequence number correctly, which the randomness makes difficult. Once the connection is open and data starts flowing, There's a second mechanism running alongside the sequence numbers: acknowledgments. The receiver doesn't just silently accept packets, it reports back. After receiving data, it sends an acknowledgment to the sender that says, in effect, "I have received everything up to this byte position." The number it sends is the position of the next byte it's expecting, which tells the sender both what has been received and where the receiver currently is in the stream. This creates a continuous feedback loop. The sender transmits. The receiver acknowledges. The sender watches those acknowledgments. If they stop arriving for a particular portion of the stream, the sender knows something went missing and can retransmit. The acknowledgments don't just confirm receipt, they give the sender a live picture of what the receiver actually has. Return to the document. Page numbers let you sort the pages into the right order. They also let you check whether any pages are missing. Sequence numbers do both of those things simultaneously. They enable reassembly. They enable loss detection. Both functions come from the same mechanism. What you can see now is that sequence numbers aren't just labels, they're a shared coordinate system, a way for two machines communicating across a network that doesn't track order to maintain a coherent understanding of where they are in the stream at all times. The sender knows which bytes have been acknowledged. The receiver knows which bytes it's still waiting for. The network in between can do whatever it does: deliver out of order, drop pieces, reroute through unexpected paths, and the two endpoints, working from their shared sequence map, can still reconstruct exactly what was sent. That's the whole point. Not to change how the network behaves, but to layer enough information on top of it that the disorder below becomes invisible to everything above.